Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to explore three of the most influential transformer models in modern NLP, Bert, GPT, and T5, and understand what each one brought to the table.
They really are the foundational family tree for almost everything we call an LLM today. Bert, GPT, and T5.
And to really get what they did, I think we have to, rewind a little bit. Look at what NLP was like before they came along.
Absolutely. The landscape was completely different. We were in the era of, well, things like word vectors.
I remember hearing about those. That was sort of the standard way to give a model some general knowledge about language, right? We had models that could recognize words.
They could recognize words, yes.
Yeah.
They provided representations. I mean, a word vector, or an embedding as it was often called, basically just mapped a word to a point in mathematical space.
The idea being that similar words like cat and kitten would be close together.
Exactly. Or king and queen.
Mm.
If they were similar, their vectors would hopefully cluster together. And that was useful, but it had a huge limitation.
Which one?
It completely lacked rich context. I mean, a word like bank, it would have one single static representation. It didn't matter if you were talking about a riverbank or a financial bank.
So the model had no way of understanding ambiguity. If I said the word pitch, it wouldn't know if I meant a baseball pitch or the tone of a sound or, tar on a roof.
Not without being specifically spoon-fed that context in a labeled data set, no. It struggled with that high-level understanding that we humans do so easily.
So the models were stuck. They couldn't really develop general-purpose knowledge. You'd have to almost start from scratch if you moved to a slightly different task.
You did. And that was the problem everyone was trying to solve. The whole goal became developing models that could learn a deep, generalizable understanding of language.
And the way to do that was through unsupervised pre-training, right? Just throw the entire internet at a model and let it figure out the rules on its own.
That was the dream. And the engine that made it possible was the original transformer architecture from 2017. Its big innovation, self-attention, was the key.
It let the model weigh the importance of every other word when it was looking at a single word.
Precisely. And that was the mechanism that finally allowed for these rich, context-aware representations. It broke us out of that static word vector world.
It's like going from a librarian who just knows the Dewey Decimal System to a researcher who has read every book and understands how they all connect.
That's a great analogy. And Bert, GPT, and T5, they all use that same foundational engine, but they specialized it in three very, very different ways. And that created three distinct families of AI.
Okay, so let's start with Bert. I feel like that was the one that really kicked off this modern era.
It was. BERT stands for bidirectional encoder representations from transformers. And the most important word in that whole acronym is right there at the beginning, bidirectional.
That sounds technical, but what does it actually mean in practice?
It means it reads text by looking both forwards and backwards at the same time. Let's go back to your bank example. If the sentence is, she walked along the riverbank to find a quiet spot. When BERT processes the word bank, it's not just looking at, she walked along the river.
It's also looking ahead.
It's also looking ahead to find a quiet spot. It sees the entire context, past and future, all at once.
So unlike older models that had to build up context one word at a time, BERT gets this holistic view instantly. It knows it's a riverbank because it saw a river on the left and the context of walking on the right.
And that simultaneous reading is what makes BERT the definitive understanding model. That's its DNA. And its architecture reflects that. It's an encoder-only model.
Okay, explain that. Why is an encoder-only setup good for understanding things?
The encoder's job is to take in some text, process all that rich bidirectional context, and then compress it all down into a very dense numerical representation.
An embedding.
So it's like a cartographer. It takes a complex landscape, the sentence, and creates a super detailed annotated map.
Perfect analogy. It's fantastic at analysis and representation, but that's where its job ends.
It's not designed to generate new text. No, not at all. The cartographer gives you the map, but it doesn't start writing a travel guide for you. The encoder produces knowledge, an internal understanding, but it's not built to create fluent new sentences. For that, you need something else.
And the way they taught it to get so good at this understanding was through something called masked language modeling, MLM.
Right, which is a type of what we call a denoising objective. It's a really clever idea.
You basically break the input on purpose and teach the model how to fix it.
Exactly. With Bert, they would take a sentence and just hide about 15% of the words. They would replace them with a special mask token.
Why 15%? Is there a magic number there?
It was what they found worked best. If you mask too few words, the task is too easy, and the model doesn't learn much.
And if you mask too many,
then there's not enough context left to make an intelligent guess. You're just guessing randomly.
yeah.
That 15% number was the sweet spot that forced the model to learn really deep relationships to fill in those gaps.
Give me an example.
Okay, imagine this sentence is, the surgeon required a fine surgical mask immediately. To figure out that the masked word is instrument, the model can't just look at the word surgical.
Right. It needs to understand the whole context, the surgeon, the urgency of immediately. It has to connect all those dots.
Precisely. It forces the model to use that bidirectional vision, to look across the whole sentence to figure out the meaning. And that training objective is what makes Bert so good at tasks that need deep analysis.
Like the big benchmarks everyone was competing on back then.
Exactly. Benchmarks like GLUE, the General Language Understanding Evaluation, these were all about analysis. Is one sentence a logical follow-up to another? Do these two sentences mean the same thing?
Things Bert was perfectly built for. Its ability to create that deep, contextual map of the text made it a natural fit.
It was. And also for question answering. That was a huge one.
You mean like the SQUAD benchmark, the Stanford question answering data set?
Yep. Bert was a beast at what's called extractive QA. You give it a long passage of text and a question, and its job is to find the exact chunk of text, the span, that contains the answer.
So it's not just knowing what the answer is, but pinpointing exactly where it is in the text.
And that requires that deep, bidirectional understanding. It was a perfect test case for Bert's strengths.
It's worth pausing here to just talk about the scale of these things. Even these early models, they weren't small. The amount of compute needed was significant.
It really was. This was the moment the field shifted from something you could do in a university lab to something that required serious industrial engineering.
We have some details on a model called StructBert, which was very similar to the original.
Right, so StructBert Large, for context, had about 340 million parameters, 24 layers deep. That's small by today's standards, but it was massive.
And to train that, what did it take?
It took a cluster of 64 high-end Tesla V100 GPUs, and they had to run in parallel for about 7 full days.
A week of nonstop computation on 64 GPUs, just for the pre-training.
Just to teach it the fundamental rules of language. Before you even started fine-tuning it on a specific task, it shows you that these foundation models aren't just clever algorithms. They're, in a way, monuments to computation.
So if Bert perfected deep understanding with its encoder-only design, the next big family, GPT, went in a totally different direction.
A completely different direction. GPT is all about creation. The G stands for generative.
The whole purpose is flipped on its head. Bert looks at text and tells you what it means. GPT looks at text and tells you what comes next.
You've nailed it. And again, that difference comes down to the architecture. GPT models are decoder-only.
Okay, so a decoder, that's fundamentally autoregressive, right?
It is. And that's the key concept to grasp. Autoregressive just means it generates text sequentially, one word or one token at a time, based only on what came before it. It's like how you type a sentence.
And this is enforced by something called a causal mask.
Yes, the causal mask is a crucial constraint. It's built into the self-attention mechanism. It makes sure that when the model is trying to predict, say, the 10th word in a sentence, it can only see the first 9 words.
It can't look ahead.
It is physically prevented from looking ahead at words 11, 12, and 13. It's blind to the future.
So if Bert is the editor, reading the whole manuscript at once to check for structure and meaning, GPT is the novelist. It's writing one word after the next, deeply influenced by the last paragraph, but with no idea what the next chapter holds.
That's a perfect way to put it. And that constraint, that causality, is what forces it to become so good at fluent generation. Its entire pre-training objective is focused on one thing.
Causal language modeling.
Which is just a fancy way of saying predict the next word.
That's it.
By doing that one simple task over and over again on trillions of words of text, it becomes an exceptional generator. It learns the statistical patterns of human language.
Which is why GPTs are so good at creative writing or chatbots or just generating long, coherent passages of text. That one objective maximizes fluency.
It's completely designed for output. And this family of models was the first to really prove what happens when you just scale things up massively.
You're talking about the shift to models like GPT-3 with 175 billion parameters. This is where we started seeing the bitter lesson of AI research in action.
Exactly. The idea that you get more reliable progress from just increasing the scale, more data, bigger models, more compute, than from clever handcrafted algorithms.
And as they scaled GPT, it didn't just get a little bit better at writing, it started doing things they didn't expect.
It started showing what we call emergent abilities.
And what does that mean in this context?
Things like zero-shot and few-shot learning. Zero-shot means you can give the model a task it has never, ever been explicitly trained on just by describing it in the prompt.
Damn few-shot.
Is where you give it just 2 or 3 examples of the task in the prompt, and it learns how to do it instantly, on the fly.
That's a massive leap. It's the difference between having to retrain a model for a week on a new dataset versus just typing, "Summarize this article for me in 5 bullet points."
It is. And that capability fundamentally changed how we thought about these models. They went from being specialized tools that needed lots of fine-tuning to being generalized AI assistants. They weren't just large language models anymore. They were becoming true foundation models.
So we have Bert, the encoder for deep understanding, and GPT, the decoder for fluent generation. Which brings us to the third major family, T5, the text-text transfer transformer.
And T5's mission was, in a word, simplification. The team at Google looked at the field and saw that it was getting fractured.
You mean you had the Bert camp and the GPT camp, and you needed different setups for different tasks?
Exactly. With a Bert-style model, you'd need one specific head for classification, another one for question answering, and so on. Every task needed its own little custom piece of architecture bolted on at the end.
Which sounds complicated and inefficient if you want to build a system that can do many things.
It was. So T5 core philosophy was just pure unification. They asked a simple question. What if we could frame every single NLP task, no matter what it is, in the exact same way?
And their answer was text to text. Everything is just input text that produces output text.
That's it. It's an incredibly elegant idea. It allowed them to use the same model, the same training procedure, the same decoding process for every single task. The specific task is just encoded as part of the input prompt.
Okay, let's make that concrete. How does something like translation fit in? That seems like a natural fit.
Translation is the easy one. If you want to translate "that is good" into German, you just feed the model an input string like translate English to German, "that is good."
And the model's expected output is simply the German text.
Exactly. The output text is "das ist gut." It's a sequence in, a sequence out.
Okay, that makes sense. But what about something like classification, where the output is usually just a single label like positive or negative? That feels less like a text-to-text problem.
You just turn the label into a word. So for a classification task like sentiment analysis, the output the model generates is literally the word positive or the word negative.
Let's take a harder one, like the MNLI benchmark. That's about classifying the relationship between two sentences.
Right. So the input would be something like MNLI premise. I hate pigeons. Hypothesis. My feelings towards pigeons are filled with animosity.
And the model doesn't output a number or a class. It just types out the answer.
Precisely. The target output text is just the single word. Entailment. The model is trained to generate the word that corresponds to the correct label. That's the beautiful simplicity of the T5 framework.
So to pull this off, the architecture had to be a blend of the other two camps.
It did. T5 uses the original standard encoder-decoder architecture, the one that was first proposed back in 2017 for machine translation.
So it has an encoder stack that processes the input?
Bidirectionally, just like Bert. It builds that rich internal understanding of the entire prompt.
And then it feeds that understanding to a decoder stack.
Which then auto-regressively generates the output text, one token at a time, just like GPT. It gets the best of both worlds. It's powerful for any task where you need to deeply understand a long input before you start generating a long output.
Transformation.
Transformation is its specialty. Summarization, translation, rephrasing. It's built for it.
And its pre-training objective was also unique. We had Bert's masking and GPT's next word prediction. T5 introduced something called span corruption.
Span corruption is another denoising objective, but it's a bit different. Instead of masking individual words like Bert did, T5 corrupts contiguous spans of text, chunks of words.
And then what happens to those chunks? This is where the sentinel tokens come in, right?
Yes. Each consecutive corrupted span gets replaced by a single, unique sentinel token, a placeholder. And this is where the big efficiency gain comes from.
Because you might be replacing, say, 5 words with just one placeholder token.
Exactly. It makes the input sequences shorter, and more importantly, it makes the target output sequences much, much shorter, which speeds up training significantly.
Can you walk me through an example?
Sure. Let's say the original sentence is, "Thank you for inviting me to your party last week," and we decide to corrupt the spans for inviting and last.
Okay, so the input the model sees would be something like, "Thank you, X me to your party, Y week."
Correct. The encoder sees that whole thing bidirectionally. And now, the target output, what the decoder has to learn to generate, is just the missing pieces, marked by their sentinels.
So it would be X for inviting Y last Z.
Exactly. Where Z is just a token to mark the end of the output. It's a very efficient way to train a sequence-to-sequence model to be flexible at reconstruction.
It's fascinating how the training objective is so perfectly tailored to the architectural goal in each of these families.
It is. And for T5's unified approach to work, it needed data, a massive amount of very, very clean data, which is why the T5 project is inseparable from the data set they created for it, C4.
The colossal, clean-crawled corpus. That name alone tells you a lot.
It does. They started with Common Crawl, which is just a raw scrape of the public web. We're talking 20 terabytes of text per month. But it's a mess. It's full of boilerplate code, ads, gibberish, duplicate content.
Just noise.
Yeah.
You can't train a high-quality language model on garbage.
You can't. So they had to build this incredibly rigorous filtering pipeline. A language purity filter, as you put it.
What kind of things did they filter out?
Oh, all sorts of things. They only kept pages that were classified as English with very high confidence. They threw out any page that didn't have at least 3 sentences. They removed lines that didn't end with proper punctuation.
So that gets rid of things like navigation menus and lists of links.
Exactly. They also took a hard line on offensive content using a block list of bad words. And crucially, they tried to remove all source code. Any line with the word JavaScript or any page with a curly brace was just gone.
That makes sense. You don't want it learning programming syntax if you're trying to teach it natural language.
And finally, they did a massive deduplication pass. They found any 3-sentence span that appeared more than once in the entire dataset and discarded all but one copy.
Wow. So after all that cleaning, how much data was left?
They ended up with C4, 750 gigabytes of reasonably clean, deduplicated, natural English text. And the big takeaway from the T5 work was that data quality at scale is just as important, if not more important, than just raw quantity.
So we've covered the 3 distinct paths these models took. Let's try to bring it all together, just really nail down the core DNA of each family.
This is the key summary. If you only remember one thing from our conversation, this is it.
Okay, first, Bert. That's the encoder-only model. Its whole purpose, its DNA, is understanding. It reads bidirectionally to create a rich map of the text, perfect for classification, analysis, QA.
Then you have GPT. That's the decoder-only model. Its DNA is all about generation. It's autoregressive, it reads left to right, and it excels at creating fluent, novel, coherent text.
And finally, T5. The encoder-decoder hybrid. Its DNA is transformation. It unifies everything into a text-to-text format, making it a powerhouse for converting one kind of text into another, like summarization or translation.
And as we've said, that specialization comes directly from the pre-training objective. The task you give the model during training fundamentally shapes what it becomes good at.
Right. Masked language modeling taught Bert deep comprehension.
Causal language modeling taught GPT fluent generation.
Then span corruption taught T5 flexible and efficient text transformation.
But there is a trade-off there, you know? That unification in T5 is elegant, but is it always the most efficient choice?
What do you mean?
Well, think about a simple binary classification task. Is a movie review positive or negative? A specialized BERT model just needs to output a single prediction. It's fast.
Whereas T5?
T5 still has to fire up its entire decoder stack just to generate the single word positive. It might be more computationally expensive for those simple tasks.
So it's a classic case of a specialist versus a generalist. BERT is optimized for one thing. T5 is optimized to do everything pretty well.
Exactly. Which also brings up the question of data. The T5 researchers actually tested this. They wondered if training on more specialized in-domain data could boost performance.
And what did they find?
They found that yes, it could. For example, pre-training on a dataset of books in Wikipedia helped a lot on reading comprehension tasks that were sourced from, well, books in Wikipedia.
That's not too surprising. If the training data looks like the test data, the model does better.
Of course. But the ultimate goal of T5 wasn't to be the best at any one specific task. It was to create a robust, generic language foundation.
So they chose the massive, diverse C4 dataset on purpose.
They did. They were willing to give up a few percentage points on a specific benchmark in order to have a model that was more broadly capable and could adapt to new, unseen tasks more easily. General competence was the priority.
This idea of scaling has come up again and again. It feels like the central theme of this whole era. The bigger the model, the better it performs.
It's what's known as the bitter lesson in AI research.
Yeah, the bitter lesson.
The finding that, time and time again, brute force scale just wins. Methods that leverage more compute, bigger models, more data, more training, almost always outperform methods that rely on clever human-designed features.
And the T5 experiments were designed to prove this, right? They asked the question, if I give you 4 times more compute, what's the best way to use it?
That's right. They compared a few strategies, training the same model for 4 times as long, or training a model that's 4 times bigger for the original amount of time, or something in between.
And what was the most effective strategy?
In almost every single test, the best bang for your buck came from making the model bigger. While training longer helped, the most consistent gains came from adding more parameters. The biggest model they tested, the 11 billion parameter T5s, was the best performer across the board.
So if you have to choose, build a bigger model rather than just training a smaller one for longer.
That's what the evidence suggested. And it's not just about the initial pre-training. It's also about what happens during fine-tuning when you adapt that general knowledge to a specific task.
How can you even tell what's changing inside the model?
There are tools, similarity metrics, that let researchers sort of peek inside the model's brain. We can compare the internal representations of the model before and after fine-tuning to see what changed.
Like seeing which parts of the brain light up differently.
In a way, yes. And they found a very consistent pattern across all 3 architectures, Bert, GPT, and T5.
Which was?
The last few layers of the model changed the most, drastically, which makes intuitive sense. Those are the layers responsible for taking all that general language knowledge and shaping it for the specific output you need for your task.
While the earlier, deeper layers,
they stay much more stable. They hold on to that core, pre-trained knowledge about grammar, syntax, and basic meaning. They're the foundation, and the top layers are the specialized tools you build on top.
Okay, let's talk about robustness. How well do these models handle messy, real-world input? Typos, bad grammar.
It's a critical question. And when researchers tested this, comparing the 3 architectures on classification tasks, they found something really surprising.
I would assume Bert, the understanding model, would be the most robust. It has that full bidirectional context.
That's the logical assumption. But it wasn't the case. The study found that GPT-2 was the most robust model overall, followed by T5, and then Bert was actually the least robust.
Wait, really? The generative model was better at handling corrupted input than the understanding model. That seems completely backwards.
It does, and it suggests that what these models are actually learning is maybe a bit different than what our neat architectural stories imply.
So what kinds of corruption were they most vulnerable to? What really broke them?
It was things that attacked the core linguistic structure. The number one most damaging change was introducing character-level errors, typos.
Okay, so they're sensitive to spelling.
Very. And the next 2 were dropping nouns and then dropping verbs.
So if you rip out the core parts of speech, the subject or the action of the sentence, the whole thing falls apart.
It does. It shows that for all their sophistication, they are still heavily reliant on specific word forms and syntactic structures. They're not reasoning about meaning in the same deep, abstract way a human does. They're still, at their core, incredibly powerful pattern matchers.
That's a fascinating vulnerability. It's a good reminder of what's really going on under the hood.
For sure. And on the flip side, they found that perturbations designed to remove gender bias had the least impact on performance, which suggests that while the models might encode those biases, their core performance isn't heavily dependent on those specific stereotypical words.
So with all this in mind, let's look at the results. T5 aimed to unify everything. Did it actually work in practice? Did the theory hold up?
It absolutely did. T5 was a massive success. It achieved new state-of-the-art results on 18 out of the 24 different tasks they benchmarked it on. It just showed this incredible level of general competence.
How did it do on the understanding tasks, the ones that were supposed to be Bert's home turf?
On Super GLE, which is a really tough collection of language understanding tasks, the largest T5 model got a score that was nearly identical to the estimated human performance level.
So it was basically as good as a person at these complex reasoning and classification tasks.
Pretty much. And on Squad, the question-answering benchmark, it also set a new state-of-the-art, even though it had to generate the answer as a string of text instead of just pointing to it.
And what about on the generative side? Summarization, translation. How did it stack up against a dedicated generator like GPT-2?
It outperformed GPT-2 on key summarization benchmarks, which, again, makes sense when you think about the architecture.
Because the encoder can read the entire long article first, build a complete understanding, and then hand that off to the decoder to write the summary.
Exactly. A decoder-only model has to try and summarize while it's still reading, which is a much harder task. We can look at one of the examples. Okay, so given a news story about a leopard trying to attack a porcupine, T5 generated this summary. Leopard tried to make lunch out of a plucky porcupine in Kruger National Park, South Africa. But the predator was put firmly in its place after the spiky creature refused to back down during a fight.
Wow. That's not just copying sentences. It's fluent, it captures the narrative, it's genuinely abstractive.
It is. There was another one about a scientific study of bacteria in homes, and T5's summary led with this amazing high-level fact. Researchers estimate that the indoor biome makes up about 0.5% of ice-free land, or about 247,000 square miles, almost the size of Texas.
That's incredible. That shows an ability to synthesize information and connect it to a real-world scale that people can understand, a truly transformative capability.
Of course, because it was a unified model, it could handle translation to German, French, Romanian, all within that same text-to-text framework just by changing the prompt. It really proved the power of the idea.
So we've seen these three architectural pillars get established. But the story didn't stop there. The GPT family, in particular, took another huge leap forward with something called instruction tuning.
Right. This was the next big insight. Even a massive model like GPT-3, which had learned so much about the world from reading the internet, was really only trained to be fluent. It knew how to complete a sentence.
But it didn't necessarily know how to follow directions.
Exactly. You could ask it to write a poem, and it might just write a factual paragraph about the subject of the poem, because that was a more statistically common pattern in its training data.
It lacked a sense of intent. So researchers realized they could fine-tune these huge models to be better at following instructions.
And that led to models like FALAN, Fine-Tuned Language Net.
What did they do differently with FALAN?
They took a big 137 billion parameter language model and fine-tuned it on a collection of over 60 different NLP datasets. But here's the crucial part. Every single training example was framed as a natural language instruction.
So instead of just showing it an English sentence and a German sentence, they would prompt it with, "Please translate this sentence from English to German."
Yes. They were explicitly teaching it to connect human language commands to the task it was supposed to perform. The goal was to improve its ability to generalize to tasks it had never seen before, to improve its zero-shot performance.
And the results were pretty stunning, right?
They were. On many unseen tasks, the instruction-tuned FLAN actually outperformed the original, even larger, 175 billion parameter GPT-3.
So just by teaching it how to follow directions, the smaller model became more capable than the bigger brute force model.
By a significant margin in some cases. It really showed that this kind of strategic fine-tuning could unlock capabilities beyond what you get from just scaling alone. And they proved that the instruction phrasing itself was the magic ingredient.
How did they prove that?
They ran experiments where they fine-tuned on the same multitask data, but without the natural language instructions. In one version, they just used a technical name, like translation, and in another, they used no prompt at all.
And what happened?
Both of those versions performed significantly worse than the full instruction-tuned FLAN. It proved that it's not just about training on many tasks. It's about training the model to understand the human intent behind a request. That's what unlocks true generalization.
It feels like this is the final piece of the puzzle. The architecture, pioneered by these three families, combined with massive scale, and now this layer of instruction following.
That's the modern foundation model recipe. It creates models that are incredibly competent and flexible. They found that instruction tuning even made the models better at learning from a few examples in the prompt, or at responding to other optimization techniques. It just creates a better, more adaptable starting point for everything else.
This has been a really comprehensive look at how we got to where we are today. We started with this basic need for better context, and it led to these three incredible, influential families.
We saw Bert, the encoder, mastering understanding. We saw GPT, the decoder, mastering generation.
And T5, the encoder-decoder, which showed us how to unify everything under one elegant, powerful framework.
And along the way, we learned these fundamental lessons about how to build language intelligence. That scale works, and that fine-tuning strategically adapts the knowledge that's already there.
And now, with instruction tuning, we've taught these models not just to know things, but to act on our intentions, performing tasks they've never seen before, just from a simple instruction.
We've gone from feeding machines data to giving them commands. And that line is getting blurrier every day.
So what does this all mean for the future roles of programming and human expertise? If a model can perform a complex task purely from a written instruction it hasn't seen before, if it can effectively write the code or perform the transformation from a plain English command, how does that change the way we interact with technology and even conceive of human skill sets? That's something truly provocative to consider as these foundation models continue to evolve. Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.